Welcome to The Explainer. Today, we're cooking up something big, like really big, the entire universe, in fact. We're going to break down the recipe that cosmologists use to build a model of everything we see, from the Big Bang all the way to the distant future. So let's just jump right in with a question that really twists our brains and gets right to the heart of all this. If the universe is expanding, what exactly is it expanding into? To get our heads around this, physicists use this fantastic analogy. Picture an infinite loaf of raisin bread dough. In this picture, the galaxies are the raisins, and the dough itself, that's space. Now, as the bread bakes, the dough starts to expand. And here's the crucial part. If you're a raisin, you see all the other raisins moving away from you. But the dough isn't expanding into a bigger oven, right? The dough is the space. There's no outside. So the universe isn't expanding into some empty void. The very fabric of space-time itself is stretching. Okay, so that's the core idea. But how do you take a concept like that and turn it into a mathematical blueprint? Let's look at the first part of that blueprint, the model for space-time itself. Well, they start with something called the cosmological principle. It sounds fancy, but it's really just two big, powerful assumptions. First, if you zoom out far enough, the universe is homogeneous. It's basically the same everywhere. And second, it's isotropic. It looks pretty much the same no matter which direction you look. Now, if you make those assumptions, it means you can describe the stretching of the entire universe with just one single variable that changes over time. It's called the scale factor, or A of t. You can think of it as the universe's zoom level. And it all comes together in this equation. Now, I know it might look a little intimidating, but the idea behind it is brilliant. This is the Friedmann-Robertson-Walker metric. The best way to think about it is as a master blueprint for spacetime, a kind of flexible ruler that has that scale factor built right in, automatically accounting for the stretching of space. So let's move on to the next part of our recipe. We've got the oven and the baking instructions, but what are the actual ingredients we're putting in this cosmic dough? It seems our universe is made of three main things. First, there's matter. That's us, stars, galaxies, plus a whole lot of mysterious dark matter. Then there's radiation, like light. And finally, the biggest piece of the pie, a strange vacuum energy, which we now call dark energy. Now here's where it gets really, really interesting. Each ingredient reacts to the expansion in a totally different way. Matter, as space gets bigger, just thins out, like you'd expect. Radiation thins out even faster because its waves get stretched and lose energy. But vacuum energy? This is the wild part. Its density stays completely constant. More space just means more vacuum energy. And this fundamental difference in how they behave, well, it sets the stage for a great cosmic battle. A tug of war between these ingredients that has dictated the entire history and evolution of our universe. And this is the rulebook for that battle. The Friedmann equation. Now don't worry about the math. Think of it like this. On one side, you have the expansion rate of the universe. On the other side, you have the total density of all the ingredients, creating gravity that tries to pull everything back together. It's the ultimate cosmic balancing act. And that balancing act gives us this incredible history of the universe. This chart tells a story. It shows the scale factor, the size of the universe, over time. And what you see is a history of shifting power, of which ingredient was winning the cosmic battle at different times. So you can clearly see three distinct eras. Way back in the beginning, the universe was this hot, dense soup where radiation was king. Then, as things cooled and expanded, matter took over, and its gravity was what allowed things like stars and galaxies to form. And then, just recently, cosmically speaking, vacuum energy became the dominant player, and it's causing the expansion to actually speed up. Okay, so this is a great story, but how do we know any of this? How can we actually see the expansion happening? Well, one of the most powerful pieces of evidence is something called cosmological redshift. So how does this work? Imagine a distant galaxy sends out a light wave. While that light is traveling across billions of years to get to us, the space it's moving through is constantly expanding. This literally stretches the light wave, shifting it towards the red end of the spectrum. The farther away the galaxy is, the more its light gets stretched. So we have the blueprint and we have the ingredients. Can this powerful model do the ultimate trick? Can it predict what's going to happen in the end? The ultimate fate of our universe? Amazingly, the model says it can. And the future of the entire universe hinges on a single number, represented by the Greek letter omega. Omega is basically the ratio of how much stuff is actually in our universe compared to the critical density. That's the exact amount needed to perfectly balance the expansion. This one number, omega, determines the very geometry of spacetime. If omega is greater than 1, there's enough gravitational pull to eventually stop the expansion and cause a recollapse. If it's less than 1, it expands forever. And if omega is exactly 1, the universe is perfectly flat and just kind of coasts. Geometry is destiny. So you can actually map out all the possible futures. This chart does exactly that. By plotting the amount of matter on one axis and the amount of vacuum energy on the other, you can see these clear boundaries between universes that recollapse and those that expand forever. So the big question is, where does our universe fall on this map? It really comes down to this stark choice. Either there isn't enough stuff, and the universe expands forever into a cold, dark, empty state, sometimes called the Big Freeze. Or there is enough stuff for gravity to win, pulling everything back together into a fiery, big crunch. So, where do we stand? Well, decades of incredible observations, from telescopes studying the afterglow of the Big Bang to distant supernovae, they all point to the same answer. Our universe is astonishingly close to omega equals 1. We seem to live in a flat universe, right on that critical dividing line. And that leaves us with a final, tantalizing thought. Our recipe is incredibly successful, but it's based on ingredients like dark matter and dark energy that we still don't fully understand. Our model points to a universe that expands forever. But what if one of our main ingredients has a secret property? A twist in the recipe that could change the ending completely.